Okay, everybody's back. Cool. So basic idea, Laplace transforms, we're all good. We're all good. Yes? Are we happy? All right, I remember to start the recording again, so we are good. Let's go ahead and take a look at what we want to be doing today. So first of all, quick definition. This one you guys should have hopefully memorized by now. And I can't see you anymore, so remember you gotta raise your hand, Bertree. The Laplace transform of little f of t, capital F of s, limit as b goes to infinity, because it's an improper integral from 0 to b, e to the negative st, f of t dt. All right, what we want to do today is look at the Laplace transform of a couple of more types of functions. So first type that we want to talk about are piecewise continuous functions. Piecewise continuous functions. Right. There's a definition in my notes, and these are again posted 4.1. So you can look at the definition in there for the technical one. So there's a definition of a piecewise continuous function. Basically, what it means is there are a finite number of pieces, and there are no vertical asymptotes. Okay. Again, more technical definition in my notes. So you can go back and look at the more technical definition in my notes if you want to, but that's the basic idea. Finite number of pieces, no vertical asymptotes. Here's the most common piecewise function that we're going to work with. There's two of them. The first one is the unit step function. Unit step function. The notation for this is u of t. It's a piecewise function, and it is going to be 0 if t is less than 0, and 1 if t is bigger than or equal to 0. Let's make that a better bigger than. 1 if t is bigger than or equal to 0. So this is called the unit step function. This is a common function that shows up in differential equations. Unit step function. If you look at a graph of this, if you look at this graph and see what it looks like. So here's my graph, right? We'll say that this is the t-axis, and then here's my function u of t. So it's going to be 0 if t is less than 0. That means I'm going to end up with 0 all the way over here. You gotta imagine that's a really thin line. And then 1 if t is bigger than 0. So that's your function. This is gonna be piecewise continuous because it has two pieces, right? Two pieces, a piece on the left and a piece on the right. Piecewise continuous, two pieces, okay? If you've got questions, virtually raise your hand and I'll call on you, but we've got this thing. We'll talk about why this shows up in differential equations when we get into section 4.2 and 4.3 for why this is useful. Right now, what we want to do is find the Laplace transform of it. So you can cheat by looking in the front of the book, or we can go back to the definition. And this one isn't actually too bad. So let's go back to the definition and figure out the Laplace transform of this. So I want the Laplace transform of the unit step function. Think about your definition for Laplace transforms and how this is going to go. We are going to have a limit as b goes to infinity, integral from 0 to b, and actually, yep, so we're going to have e to the negative st, f of t dt. And I want u of t instead of f of t. So since the function I'm doing is u, I want u of t, not f of t. All right, remember that here's my function. U of t is a piecewise function, so it's 0 if t is less than 0, and it's 1 if t is bigger than or equal to 0. So if I'm doing this integral, for this integral right here, I have that t is less than or equal to b, and it's bigger than or equal to 0. That comes from your limits, right? You've got limits on your integral from 0 to b, so therefore t is between 0 and b, because those are my limits on my integral. So if I'm working on t between 0 and b, then I know that u of t is just equal to 1. I don't have to worry about the 0 part at all. I just am worrying about the 1 part because I'm in this part where t is bigger than or equal to 0. This then is going to give me limit as b goes to infinity, integral from 0 to b, e to the negative st times 1 dt, right? If I were having t values be less than 0, then I'd have to use the 0 part, but I don't. I just have t values between 0 and b. And this is exactly the same thing as the Laplace transform of 1. Think about this 1 right here as your f of t, right? That's exactly the same as the Laplace transform of the function 1, and that we did yesterday, and it's just 1 over s, and remember that this is for s bigger than or equal to 0. So the upshot of this, and you can find this in the table in your book, is that the Laplace transform of this cool unit step function is just 1 over s for s bigger than or equal to 0 by using the definition of the Laplace transform. That's the one we just did. For the 850th time, section 4.1 is getting us comfortable with Laplace transforms. So now we have the Laplace transform of this unit step function that we are going to use when we get into differential equations. Daniel.
Is it because if s is equal to 0, it's like undefined? So
Yeah, when we talk about Laplace transforms, we're dealing with integrals. And so remember, when we're dealing with integrals, we don't worry too much about what happens at the endpoints. So yes, technically you're correct. When s is equal to 0, this is undefined. But we're going to say, I don't really care all that much what happens at the endpoint. So s bigger than 0. S bigger than or equal to 0, or it would be more accurate to say s bigger than 0. Either way, endpoints don't matter quite so much with integrals. Okay.
Okay, thanks.
Nope, totally good question. All right, other questions? Anything else before we keep going? I can't see you. So anybody else? Other questions? Doing good? We'll go with doing good. Okay. All right, this is boring because what we want is to be able to have a step somewhere else. So we've got this new function and we're going to call it u sub a of t, or sometimes the book also uses u of t minus a. This is the unit step function. With a jump at, instead of t equals 0, it's going to have a jump at t equals a. So we're basically taking the same unit step function that we just had and we're making it more general. We're going to say the jump can occur any place that I want. Instead of having a jump at 0, I can have my jump occur anywhere I want. And so we'll say we can have maybe a over here. So then this thing will go to 0 to the left. Here's 1, and it'll be 1 going out to the right. So it can look like that. A can also be negative. That's totally allowed. So we could have a negative value of a over here. And then once again, this thing is going to be 0 to the left of a. And then here's 1, and it'll be 1 going out to the right of a. So a could be 0, it could be negative, it could be positive, either way. We're just making this unit step function a little bit more general. Piecewise, unit step function sub a is still a piecewise function. So it's going to be 0 if, and in this case, it's t is less than a, and 1 if t is bigger than or equal to a. So it's the total same function as what we just had, except that my jump happens at a instead of at 0. Total same function, we're just making it more general. We're saying my jump happens at a instead of happening at 0. That's the only difference for this. Okay, give me just a sec. I'm going to stop sharing my screen because I want to pause the recording and start it again.